Alright guys, we're gonna continue our discussion, and now we're going to address basically impacts and oblique impacts basically. Alright guys, so what you know about impact and momentum now should basically be the following, right? If you have an object that is flying with some velocity or some momentum, then the object is going to have this momentum, which is m times v. That object will continue to go in this direction forever, unless at some point basically this object is subject to some force or impulse, fdt. If the force is very small, then we can model it by fdt. If the force takes some time, then we're going to integrate this impulse from 0 to tf, which is the time of the impact. And now basically this object is going to be going with, by summing these two vectors, this object will be traveling with this mv2. Okay, this is the updated momentum of the object, and then now it's going to keep flying in this direction unless we apply some more momentum, and then we're going to change its direction. So this is how momentum and impulses basically work. And we said in the case of two objects which are colliding, when this object hit that object, basically this guy was traveling with this momentum, and now the interaction force between them is equal and the opposite. So this guy is going to have fdt like that, and this guy will have no initial momentum, but this guy is going to have maybe fdt, assuming this ball started from rest. Fdt will cause this guy to be moving with mv, right, which is this momentum. Okay, so momentum is always equal to the impulse and whatever previous momentum that you had. Alright, so let us look at impact and central impact. So central impact is basically when two objects basically are colliding, and in this case basically this guy is coming to the left and then A is going to the right, and then I can do my momentum equation on both of them, and then I can find the velocity of A and B after the impact based on what we described in our last lecture. Today we are going to look at the oblique impact. The oblique impact is when A and B are basically colliding at this plane of contact, and then after this basically A would be going like that and then B may be going like this. And here's what is going to happen. So as you guys know, the interaction force between A and B are going to be along this direction. This is called the line of impact, which is what? Perpendicular to the tangent. Okay? This is your line, and then this is your tangent, and then the line of impact will always be perpendicular to the tangent. So along the plane of contact, so if I label this guy X and then I'm gonna make this guy Y, along the y direction basically I have no forces, because the forces will only live in the line of contact. So the momentum of A is actually going to be conserved along the y direction before the impact and then after the impact. Similarly for B, the momentum will be conserved in the y direction. So the mass of B times the velocity of V before the impact in the y direction is going to be equal to the mass times the velocity of B in the y direction after the impact. But along the line of impact basically we are going to have fdt, right? But then luckily if you take the whole system, then fdt will cancel out because that impulse will be equal and the opposite, and you will not basically incorporate that into your equation. Alright, so this is what I just mentioned here, right? So you know we have this is before the impact, this is during the impact. And by the way, we are using impact, we're not using the energy, because you have losses that occur during the impact, and we don't want to worry about these losses. This is why we are using that impact equation. Okay guys, so I think what I'll do is let us go directly to the heart of it, and then quickly derive this for you guys, and we will go from there. Alright, so okay, so let us take the situation of an oblique impact, and in the case of the oblique impact you're going to have this and then that. If I have this ball that is coming like that, and then this ball is coming like this, this is A and then B, VA1, VB1, I know these two are going to collide and then they are going to go upward. So if I actually draw the impulses on A, so basically A, it had this momentum MVA1 plus basically it's going to be here, and now it's going to have FDT that is due to the collision, and then after this it's going to be traveling with MAVA2. You guys agree? And base B, basically this is ball B, it was traveling with this momentum MVV1 plus on B it's going to have this, it's going to be now traveling with MVV2. Alright, and these are vectors, so we can sum them in any direction that we want. So I'm gonna sum the impulses on A. What do I get if I'm summing the impulses in the upward direction? So FDT is going to be horizontal, and then again these are the same units. So I'm going to have what? MA, right? This is MA, by the way, right? MA, A, and this guy is MB. I'm going to have MA, VA, 1, Y, right? I can take the vertical velocity of A. I have no impulse in this direction, and that is going to be equal to MA, VA, 2Y, right? Because I have the same mass, and then I'm going to end up with VA1Y is going to be equal to VA2Y. So during an oblique impact, A and B, they will both basically have the same velocity along this tangent, right? Along this is a tangent line, and then this is line of action, usually abbreviated as LOA. Alright, if I sum the impulses, and notice how I'm summing the impulses. So this is a notation that you use. And B, what do you get? So you are going to get MA VA1 X, right? MA VA1 X minus FDT is going to be equal to what? So now this guy is going to be in opposite direction. It's going to be equal to, I'm going to assume everything is positive now, because I don't know if this guy will actually continue to go to the right or to the left. So let's just keep it positive, and then later on we're going to count our equations and our unknowns, and then if you solve VA2X to be negative, then we know it has rebounded. This is on B, I'm sorry, this is on A, right? Now on B, if you sum the impulses in the upward direction on B, what do you get? You're going to get a similar result, so you're going to get VB1Y is going to be equal to VB2Y. And if you sum the impulses on B in the right direction, you are going to get what? You are going to get, what? Minus, right? So it would be, so we're looking at B, right? So it will be minus MB VB1 X, because it's coming in this direction, plus FDT, so we're looking here, right? Plus FDT is going to be equal to what? MB VB2X. So this is equation 1, this is equation 2. I'm sorry, this is equation 2 right here, and this is 3, and then this is equation 4. So if I sum 2 and 4 together, I'm going to be able to actually cancel FDT, right? You guys agree? And so here basically I put minus, right? I put minus because I assume that VB is actually coming toward the left. But what I would like to do is actually, I'm going to actually keep this positive for you guys. And the reason why I want to keep this positive, I'm going to assume that all the velocities are, you know, positive in the right direction. So if this guy was negative, then here it would be simply be negative. That way you will make sure that all the signs are in a positive X, and then when you solve for them, if they are negative, then they would be in opposite direction. Right, because the impact could also happen if this guy was coming like this and then this guy was also coming, but at a faster velocity, it will still hit it. Alright, so VBs are positive in this case. So if I sum 2 and 4, FDT will actually cancel out. Then I'm going to end up with what? MA VA1X plus MB VB1X is going to be equal to, and if you remember, this is the equation that we had on 2 balls earlier. that are hitting each other. So MA VA2x plus MB VB2x. Alright, so basically the initial momentums of the system in the x direction is going to be equal to the final momentums of the systems in the x direction along the line of impact. So basically we have really so far developed three equations, right? Because this guy is these two equations together. So we have three equations, 1, 2, and then 3. How many unknowns do I have? So I'm going to assume that I know VA1x, VA1y, VB1x, VB1y, and I'm going to try to solve for the rest remaining for unknowns. How many unknowns I have? The velocities of A and B in the two directions, x and y. So VA2y, VB2y, VA2x, and then VB2x. Again, so velocity of A2, so VA2 is unknown, VA2 in x and y, and then VB2 in x and y. So total is, how many? We have 4 unknowns, and we need 4 equations. So far we have 3 equations, we need 1 more equation to be able to solve the problem. So that last equation is going to be introduced to you right now, and then this equation is actually called the coefficient of restitution. The coefficient of restitution basically is a number that defines the collision or the ratio of the velocities after the impact, and this is given to you by E. And if I have two balls, A and then B, they were traveling, so this is VA1, VB1. After the impact, again, I'm assuming this is my positive direction, VB2. My coefficient of restitution is going to be equal to VB2, and the coefficient of restitution, guys, only applies along the line of action. So be very careful that the coefficient of restitution only applies along the line of action. So in this case, this is my line of action. So VB2, in our case, the line of action is going to be along the x direction, right? So it would be what? VB2x minus VA2x divided by, and this is the definition, VA1x minus VB1x. Alright, VB2x minus VA2x divided by VA1x minus VB1x. Alright, and the coefficient of restitution basically defines like the rebounding characteristics of the collision. If VB, let's say, was a wall, if V was a wall, like it had no initial velocity, so VB1 and VB2 are 0, then assume like if B is fixed, alright, then, and the coefficient of restitution is a known, so that would be given to you, then I want to be able to solve for a VA2x, right? If B was a wall, then VB1x was 0, and then VB2x is 0, then I can solve for VA2x. It would be what? Minus, in that case, VA2x would be minus E VA1x. So basically, if I'm trying to hit a ball on the wall with some velocity VA1, I know my velocity in after the collision is going to be equal to minus, because the ball will rebound, right, with VA2, and it's going to be proportional to VA1. E is usually less than 1. It's always less than 1, right? So if E was 0, the coefficient of restitution is 0.5, then the ball will rebound with half the velocity that it was thrown on the wall. If the wall had some velocity, then basically I'm going to reduce this, and then I'm going to be able to solve the final velocity of the wall or the ball after this. But this is this has two unknowns, so this equation has two unknowns. So if I add this equation to my previous 3 equations, then I'm going to have how many equations, how many unknowns? I'm going to have 4 equations and 4 unknowns, right? So 1, 2, so I know the velocities of these 2 balls after the collision along this direction, they will both be equal, right? It won't change because I have no impulse. I'm not applying any force in the upward direction to change their velocities, but I know along the line of impact basically their total momentum is going to be conserved. And then I'm going to say MAVA1x plus MBVB1x is going to be equal to MAVA2x plus MBVB2x. Alright, so these give me 3 equations, 3 unknowns. I need one more equation, which is the coefficient of restitution, and then that is the equation of the coefficient of restitution. And by principle, the coefficient of restitution is really defining if you were to actually measure the coefficient of restitution. Let's say you have a basketball, you let go of the basketball, it hits the ground, and it goes up. And basically, if you measure the velocity of the ball before it hit the ground and then the velocity of the ball right after it hit the ground, then you can measure E, right? And then here the signs are already taken care of here, right? By here saying VA2x is equal to minus EVA1x, basically you are taking this quantity as sort of like a vector because now it has a magnitude and then direction, right? So this, if VA2x is positive, it means that VA2x is along VA1x, right? And negative, then vice versa. Alright guys, so we learn in this course by doing, so I think the best would be to go from here and then do an example. This basically sums up what I just described, right? First equation, conservation of linear momentum. This is what we just did. And this is along the x direction, right? Along the line of impact. So this equation is along the line of impact. The momentum is conserved. Coefficient of restitution, which is what I just defined. So this is given to you. If E was equal to 0, in the case of a ball and wall, then you would be stuck to the wall. You would not come back from the wall. Elastic impact, E is equal to 1, then forget about what they mean here by no energy loss, but E is equal to 1, basically the velocity coming backward is going to be equal to the velocity going forward, which is why the energy is not lost. Typical values of E are steel on steel 0.5 to 0.8, lead on lead 0.12, 0.18, wood on wood is this, glass on glass. So these are good, those of you who later on end up working in design and industrial design and things like that, where you are brainstorming and developing prototypes. Might be a good idea to know these factors as you are developing prototypes. Alright, okay, this is what I just described. You have 4 unknowns, which are what? VA2x, VA2y, VB2x, VB2y. You need 4 equations. 1, 2, 3, and then coefficient of resistance is 4. Be careful about how the coefficient of restitution is applied. You always do this, right? So we have A and then B. A is chasing B. A has VA1, B has VB1. E is always the final velocity B2 minus VA2 divided by VA1 minus VB1. Okay, always remember that the bottom of this will be VA1 minus VB1, and on top it will be VB2 minus VA2. It's like opposite, but just know this equation, and I'm gonna provide you this equation at the time of the exam. So you don't need to memorize it. You need to be aware of it, and then you need to know how to apply. Alright, so I think guys we can do right now an example on this, and this is your example. I'm sorry, this is your example, example 6. Alright guys, so in this example what we have is we have 2 smooth spheres, they hit each other, they have, each one has a mass m, and the coefficient of restitution between the two, between any collision is E. So this ball is going to hit that ball is going to hit that wall, and then it's going to rebound. And initially A is given a velocity of V0 and B was at rest. So this is A and this guy is B. How do you know the velocity of B after it actually strikes the wall? So we have to apply this on both of them, right? How do we solve this problem? How many unknowns do I have? So the first thing that you can apply here is conservation of momentum, right? Before and after the impact. And then this is like doing, what I mean by conservation of momentum, I'm basically doing the momentum and impulse equation on ball A and then ball B, and then I'm summing them up. And I know FDT and FDT will cancel out between them. And then I'm going to end up with what? MA, right? VA1. There's no need to include X or Y. It's going to be equal to what? MA VA2 plus MB VB2, right? So this is the final momentum of the system. I have 2 unknowns, 1 equation. I need 1 more equation. So that equation is going to be E is equal to what? We said it's going to be equal to VB2 minus VA2, divide that by VA1 minus VB1. Alright guys, so now we have 2 equations and then 2 unknowns. Now I will be able to solve for the velocity of B2, right? And also VA2. How do we do this? So just, it's algebra, right? VB2 is equal to E So VB2 is equal to E multiplied by this plus VA2. Take this guy and then plug it here. You're gonna end up with what? MA VA2 plus MB, the whole thing, E. Okay, now I'm gonna be able to solve for VA2 from here. So what is that? So MA VA1 is equal to MA VA2, and here the balls basically have the same mass, so we can basically remove the mass, right? Plus multiply these two together, right? So we're gonna end up with let me actually remove M because this will simplify the problem, I think. So when I remove M, and then you're gonna end up with what? VA1 is equal to VA2 plus EVA1 minus EVB1 plus VA2, right? Okay, so now what? Now we're trying to find VA2. Okay, VA1 1 minus E equal to 2VA2, right? 2VA2 and then EVB1 will be here, right? EVB1. So then VA2 is going to be equal to okay, so now so VA2 is equal to EVB1 plus VA1, and in our problem we had VB1, the initial velocity of ball B was 0, right? So you're gonna end up with VA1 1 minus E, and then divide that by 2. So this is the final velocity of A, and now we need to find the final velocity of B. So here we know that based on the conservation of momentum, we had MVA1 was equal to, I'm going to remove the mass because it is equal for all of them, plus VB2. We need to find VB2. So VB2 is actually equal to VA1 minus VA2, which is VA1 minus VA2, which is this guy, or 2 VA1 minus VA1 plus E VA1, which is equal to what? It's going to be equal to VA1 E plus 1 over 2. Okay, so this is going to be your VB2. So the final velocity of B after the impact is going to be equal to VA1 E plus 1 over 2. So if the impact is fully elastic, then E is equal to 1. Then VB2 would be equal to VA1. So which makes sense, right? So if this guy is traveling, right, and then if those two have the same mass, and if ball B was initially at rest, then the final velocity of V will actually equal to the velocity of A, and if if the elasticity is equal to 1, then VA2 is going to be equal to actually 0. So basically what happens is if the two balls have the same mass and the coefficient of restitution is equal to 1, and this guy is going to hit this guy, then this guy will hit it, it will stop, and then now B will start moving with the same velocity as A. But obviously here it clearly appears in the mathematics of it. Alright, so here's how you find the velocity of B after the collision. Now if you would like to find the velocity of B after it hits the wall, and we already just did that, right? So this is B, and now we know that VB2 is traveling with that velocity. So after the impact, so we have a wall, so VB3, which is the velocity of B after the impact, is going to be equal to what? Minus E. We already developed this, right? Minus E multiplied by, so VB3 minus E multiplied by VB2, right? And then this comes from the coefficient of resistance equation, which I just described earlier. You can treat the ball as a mass, and then it has a zero mass. Then VB3 is equal to minus E multiplied by VB2, which is basically equal to minus E multiplied by that number, VA1, 1 plus E, divide that by 2. Okay guys, so that is really it in terms of this example. If you have any questions guys, please go ahead and let me know, send me an email and we can interact on that.